Listen, you hold two pieces of metal in your hands. You push them towards each other and suddenly, bam, you feel it. There is something between them, some kind of spring, some kind of rubber band that you cannot see. And you ask me, Richard, why do they repel? And I look at you, and I know what you are waiting for. You are waiting for me to tell you, well, it's like there are little rubber bands inside, or it's like water flowing through a pipe. You want me to explain the unknown in terms of something familiar, in terms of something you understand, but I cannot do that. I am not going to lie to you. The problem is not the magnets. The problem is your why. Have you ever thought about how slippery that question is? Here's an example. My Aunt Minnie. She slipped on the ice and broke her hip. We take her to the hospital. And someone asks, why is she in the hospital? The answer is simple. Because she slipped on the ice. You are satisfied with that. You nod. You understand. But wait. Why is ice slippery? Well, you might say, because when you step on it, the pressure melts the water and you get lubrication. And I will ask, but why does ice expand when it freezes, while everything else contracts? And suddenly we are talking about the crystal lattice, about hydrogen bonds. Why do hydrogen bonds work that way? Do you see what is happening? The more you ask why, the further we get from Aunt Minnie and her hip. We wander into a wilderness where there is no ice, no hospitals, no people, only atoms and the void. So let's go back to the magnets. You feel a force pushing your hands apart. And it seems strange to you because you cannot see it. It seems like magic because it happens at a distance. But let me ask you a counter question. Be honest. Why are you not falling through that chair right now? Look at your butt. Look at the chair. Look at the... Why don't you pass right through it, like a ghost through a wall? You will say, because the chair is solid. But what does solid mean? If we look at the chair under a microscope, we will see emptiness. Atoms are almost entirely empty space. A tiny nucleus and electrons somewhere far away in orbit. If the nucleus is a pea in a stadium, the electrons are flies in the stands. Everything else is empty. So why doesn't one emptiness, your body, pass through the other emptiness, the chair? The answer will shock you. It is the exact same force. The exact same force that pushes the magnets in your hands is, right now, holding your butt on that chair. It is the electrical force. In reality, solidity does not exist. There is no such thing as contact. And when you knock on a table, your atoms never, do you hear me? Never actually touch the atoms of the table. They get close, they feel a wild repulsion, and they bounce back. Does it hurt when you punch a wall? It's not the wall hitting you. It is the electromagnetic field of the wall hitting the electromagnetic field of your fist. So when you ask me, why do magnets repel? I answer, and why doesn't everything else repel just as noticeably? In magnets, we just see this hidden force exposed, amplified, dragged out into the open. It is not an exception to the rule. It is the rule. It is the force that holds the world together. And to understand it, we have to forget about rubber bands and springs. We have to go down to where common sense stops working. Are you ready? Then let's see what reality is actually made of. Let's stop for a second and think about this. You sit there looking at me and you think the world around you is solid. You pick up a cup of coffee and it feels solid. The table is solid. The floor beneath your feet is reliable. But this is the greatest illusion nature has ever created. If you had eyes capable of seeing the atomic scale, you would lose your mind with fear, because matter is an incredibly loose thing. Imagine an atom. If we blow up the nucleus of an atom to the size of an apple, do you know where the electrons would be? They would be flying a kilometer away from that apple, a kilometer of emptiness. Everything you see around you is emptiness, lightly seasoned with matter. So why don't you fall through the floor right now? Why doesn't this coffee cup pass through the table? The secret is in the electric charges. The outer shell of every atom is electrons. They are negatively charged. And the table has electrons too, and they are also negatively charged. And what do like charges do? Correct. They hate each other. They repel with a fury you cannot even imagine. When you put the cup on the table, the electrons of the cup start to approach the electrons of the table, and a real storm begins. The electric field screams, "Back! Do not come closer!" And the cup hovers. It floats. In fact, between the bottom of your cup and the surface of the table, there is a gap. A tiny gap. Maybe 1 angstrom. But it is there. Not a single atom of the cup ever touches an atom of the table. You have been hovering above the ground your entire life. You have never, not once in your life, truly touched anything. What you call the sensation of touch is just your nerve endings, registering the pressure from this electric field. You feel the force, not the matter. And thank God this force is so powerful. Because if I snapped my fingers right now and turned off the electromagnetic interaction, do you know what would happen? You wouldn't just fall. You would cease to exist as a structure. Without the electrical repulsion keeping your atoms apart, your flesh, your bones, this chair, this house, everything would collapse into a cloud of microscopic dust. And then gravity would pull it all to the center of the earth. Speaking of gravity, you think gravity is a big force? It holds the planets? It holds you on the ground? But look at this. I take a little magnet, a regular one, from the fridge, and I bring it close to a paperclip lying on the table. The paperclip jumps up and sticks to the magnet. Think about what just happened. The entire Earth, this gigantic machine weighing billions of trillions of tons, is pulling the paperclip down. The gravity of the entire planet is working against the paperclip. And me, I'm just holding a tiny piece of metal. And this little magnet defeats the entire planet. Click, and I have the paperclip. That is how much stronger electromagnetism is than gravity. It is a number with 40 zeros. If your left hand had 1% more electrons than protons, and your right hand had the same, the force of repulsion would be enough to lift the weight of the Empire State Building. No, I'm lying. Not the Empire State Building. That force would be enough to lift the weight of the Earth, just from a tiny imbalance of charges in your hands. But nature is smart. She keeps everything in balance. Plus and minus give zero. Almost everything around us is electrically neutral. Protons are balanced by electrons. That is exactly why you don't explode and why you don't stick to the ceiling. This monstrous force is hidden. It is locked inside the atoms. It is busy holding matter together. And here we come to the main question. If everything around us is made of electricity, if every piece of wood, plastic, or copper has these billions of charges, then why don't they act like magnets? Why doesn't copper attract paper clips? Why doesn't wood stick to the fridge? What is so special about iron? Oh, the answer to that question is beautiful. It lies in movement, and in how one Scotsman in the 19th century saw a connection that no one had seen before him. So we have this crazy electric force, pluses and minuses. They attract and repel. We got that. But where does the magnet come from? You look at a magnet and you don't see any batteries. You don't see wires. Where's the electricity? Here's where the history gets interesting. For a long time, people thought that electricity and magnetism were two different things, like, say, light and sound, different phenomena. But in the early 19th century, someone noticed something strange. If you run a current through a wire, just regular electricity, flowing electrons, a compass next to that wire goes crazy. The needle twitches. Wait, the electricity moves here and the magnet turns there? That means a moving charge creates a magnetic field. Remember this, magnetism is a consequence of the movement of electricity. A static charge creates an electric field. A moving charge creates a magnetic one as well. And then came the Scotsman, James Clerk Maxwell. In 1873, he did what I consider the greatest achievement in the history of human thought. Bigger than the pyramids, bigger than the moon landing. He took all these scattered rules about electricity and magnets and combined them into 4 equations, 4 lines. And these lines told us, guys, there is no electricity and magnetism. There is electromagnetism. It is one entity, a two-faced Janus. Here's an example that blows the mind. Imagine a wire with a current. Around it there is a magnetic field. We have measured this. Now imagine that you shrink down to the size of an electron, and you fly alongside that wire at the exact same speed as the current inside it. For you, the electrons in the wire have stopped. You are flying alongside them. Relative to you, they are stationary. And if they are stationary, there is no movement. That means there is no magnetic field. The magnetic field has disappeared. But wait, the force hasn't gone anywhere. The wire still attracts or repels other charges. But if there is no magnetic field, what is it? For you, flying alongside, it has turned into a pure electric field. This is Einstein before Einstein. Magnetism is just electricity seen from a moving frame of reference. It is a relativistic effect. Do you understand what this means? When you hold two magnets in your hands and feel them pushing apart, you are actually feeling space and time distorting due to the motion of charges. You are feeling the theory of relativity in the palms of your hands. Maxwell gave us more than just that. When he solved his equations, he found something else in there, a wave, an oscillation of electric and magnetic fields that support each other. One creates the other, and they run forward. He calculated the speed of this wave, and his jaw dropped. The speed matched the speed of light. Light is an electromagnetic wave. The light by which you see me now, the radio waves in your phone, the X-rays in the hospital, the heat from a radiator, it is all the same thing. It is the vibration of the very same force that keeps you from falling through your chair. We live in an ocean of electromagnetism. But let's go back to our question. I promise to be honest. We said that a magnetic field is created by a moving current. We take an electromagnet, a coil of wire, run a current through it. It works. It all makes sense. No, but look at a regular piece of iron. A permanent magnet. Where are the wires there? Where's the battery? It is cold. It is solid. It sits on the table for years and doesn't run out of power. Where's the movement inside it? What is spinning in there? If I cut a magnet in half, I won't find a little power plant inside. So where does the current come from inside a dead piece of metal? The answer lies where classical physics ends and real magic begins. We need to look inside the atom itself. So, we are looking for the current. We are looking for the movement of charge inside a dead piece of metal. And of course, you have already guessed where it is. It is in the atoms. The electron orbits the nucleus. Charge moves in a circle. Bingo. That is a tiny current loop. That means every atom is a little magnet. But that is only half the story. Actually, less than half. There is something else. The electron itself. Imagine the electron as a little ball, spinning on its axis, like the Earth, or like a spinning top. Since it is charged, this rotation creates a magnetic field. Physicists call this spin. Now I have to warn you, if you ask a quantum physicist if the electron really spins like a ball, he will start getting nervous. He will say, well, not exactly, it's an intrinsic property. But for us right now, yes, it spins. It is a tiny, eternal magnet. Wait, if every electron in the universe is a magnet, and you are made of electrons, and this table is made of electrons, why doesn't everything stick to everything else? Why aren't you a magnet? Why, damn it, is magnetism such a rarity? Here the great equalizer of nature comes into play. Symmetry. In most materials, electrons live in pairs. It's the Pauli principle. But let's not complicate things. The point is that if one electron spins right, its neighbor must spin left. One has its north pole up, the other down. Plus and minus. They kill each other's magnetic fields. They cancel each other out perfectly. Your body, wood, plastic, copper, they are full of electrons. But all these electrons are married. They are busy with each other and ignore the outside world. But there is iron, and nickel, and cobalt. These are the rebels of the periodic table. They have bachelor electrons on their outer shells. Unpaired electrons. They have no one to cancel them out. They spin, and their magnetic fields add up. Every iron atom is truly a powerful magnet. Aha, you will say. But Richard, I pick up a nail. It is iron. It has these bachelors. But it doesn't attract paper clips. Why? Because nature loves chaos. Inside the nail, the iron atoms are grouped into neighborhoods. We call them domains. In one neighborhood, say 1,000,000 atoms, everyone has agreed, we are looking north. Great. But in the next neighborhood, 1,000,000 atoms say, no, we are looking east, and others, south. It's like a crowd of people in a square. Everyone is pushing, looking in different directions. The sum is zero. The nail as a whole is neutral because its internal neighborhoods cancel each other out. But then you take a real magnet and bring it close to the nail. What happens? The magnetic field begins to convince these domains. It's like a general walking out in front of the crowd and shouting, "Attention! Face right!" And the borders of the domains begin to shift. Those who were looking in the right direction grow. Those who were looking the wrong way disappear. And suddenly, click, all the billions of trillions of atoms line up. Their fields add together. Now the nail has become a magnet itself. That is what a magnet is. It is simply a piece of matter where we manage to enforce discipline, where we manage to make chaos march in formation. But know this discipline is fragile. Inside the metal, there is an eternal war. On one side, magnetic forces that want order, everyone looking the same way. On the other side, heat, thermal energy. Heat is shaking. Atoms vibrate. The hotter the nail, the harder it shakes. Heat tries to break the formation, to knock the electrons out of alignment. If you heat a magnet enough, to the Curie point, heat will win. The shaking will become so strong that the electrons won't be able to hold the line. Magnetism will disappear. Order will collapse into chaos. So when you see a magnet, you are seeing a frozen moment of order's victory over thermal chaos. We explained how. Spins, domains, orbits. But remember where we started? I promised to explain how one magnet feels another. How do they communicate across the void? What flies from one to the other saying, "Move over"? Here classical physics throws its hands up. Here we enter the twilight zone. Here live particles that shouldn't exist. So we have two electrons, one here, one there. They repel. In the 19th century, people said, well, it's a field. They drew lines on paper and calmed down. For them, a field was something like jelly or an invisible fluid smeared through space. But then came quantum mechanics and said, hey guys, there is no smoothness in nature. Everything is made of chunks, of portions, of quanta. Light is particles, photons. Matter is particles, electrons. That means the field itself. The force itself must consist of particles. Sounds logical, right? When one electron pushes another, it doesn't use telepathy. It has to throw something at it. Imagine two people on an ice rink. They are standing on the ice. One throws a heavy basketball to the other. To throw the ball, the first one has to recoil backwards. Recoil. The second one catches the ball, and the impact pushes him backwards. They drift apart. They repelled each other without touching hands. The ball is the carrier of the force. In the world of electricity and magnetism, this ball is a photon, a particle of light. Yes, you heard right. The very force holding the magnet on the fridge is an exchange of light. Electrons are shooting photons at each other. But here, being smart people, you should stop me and say, Richard, are you crazy? If magnets were constantly shooting light, they would glow in the dark. They would lose energy and disappear. And you are absolutely right. If these were ordinary photons, the universe would fall apart. But nature is trickier. She uses what I call virtual photons. Here's where the real magic of quantum electrodynamics, or QED, begins. This is my favorite toy. Look, there is this guy, Werner Heisenberg, and he has an uncertainty principle. Roughly speaking, this principle allows nature to cheat a little bit. It states you can violate the law of conservation of energy. You can take energy literally from nowhere, borrow it from the vacuum. But there is a condition. You must give it back very, very quickly. The more energy you stole, the faster you have to return it. It's like bank fraud. If you stole $1 million from the vault but put it back a nanosecond later, before the audit came, no one would notice anything. No crime occurred. So the electron does exactly that. It borrows energy from the void, creates a photon, and fires it. This photon flies out, hits another electron, and disappears. It returns the energy back to the universe. It existed exactly long enough to deliver the kick. We cannot see these photons with our detectors. They don't fly into your eyes. They live only between charges. They are ghosts, but the momentum they transfer is quite real. Think about it. Right now, inside your body, inside every atom, Billions of electrons are playing this insane ping pong. They are juggling ghostly particles of light that exist for only an instant, and all this bustle, all this chaos of exchange, creates what we perceive as a calm, reliable, solid reality. A magnetic field is not a fog. It is a storm. It is a hurricane of virtual photons. I drew special pictures for this, diagrams that now bear my name. Just sticks and arrows. A straight line is an electron. A squiggly line is a photon. Where they meet, an event occurs. It looks like a child's scribbles, but these scribbles allowed us to calculate the behavior of matter with frightening precision. We used to think of physics as a clockwork mechanism. Gears turning, everything predictable. QED showed us that under the hood of reality, there is a total mess. Particles pop in and out of existence. They travel all possible paths simultaneously. They do everything that is not forbidden, even with a tiny probability. To find out how a magnet will behave, we have to sum up the probabilities of all these crazy paths. And when we do that, when we sum up all this chaos, a miracle happens. The answer converges. And it doesn't just converge. We obtained a theory that is the most precise thing ever created by the human mind. You have no idea how precise it is. You have every right to look at me skeptically. I just told you that space is boiling, that particles borrow energy from the future, and that reality is the sum of all possible madnesses. You could say, Richard, this is just mathematical gymnastics. This can't be reality. You theorists are just playing with formulas. And I would agree with you, were it not for one number, the magnetic moment of the electron. Look, an electron is a magnet. We established that. It has strength. How strong is it? According to the old theory by Paul Dirac, which didn't account for this virtual mess, the strength factor, G factor, should be exactly 2. Exactly. $2,000. Simple and elegant. But quantum electrodynamics says no. It says that because of that cloud of virtual photons constantly buzzing around the electron, because the electron interacts with itself, its magnetic strength should be just a tiny bit higher. How much higher? Well, we sat down and calculated. It was hellish work. We drew hundreds of diagrams. We accounted for how a photon splits into an electron-positron pair, how those emit photons again. We calculated for years, and at the same time, experimentalists in their dungeons built traps. They caught a single lonely electron and made it dance in a magnetic field to measure its strength directly. And here is the moment of truth. The experimentalists come and put a number on the table, 1.01, and more digits. And we, the theorists, with trembling hands, unfold our calculations. 1.01. Do you realize what happened? They matched. They didn't just match roughly. They matched to the 12th decimal place. To help you understand the scale of this achievement, imagine you are measuring the distance from New York to Los Angeles. That is about 4,000 kilometers, or 2,500 miles. And you measure it with such precision that your margin of error is less than the thickness of a human hair. The distance across the entire continent, accurate to a hair. That is how good quantum electrodynamics is. It is the most precise prediction in the entire history of science. Not biology, not chemistry, not even Einstein's gravity can boast such devilish precision. When I see these numbers, I get goosebumps. It means that all this crazy story about virtual photons, about violating conservation laws, about borrowing energy, it is all true. Nature really works like that. We didn't invent it. We peeked at it. We found the key to the safe where nature keeps her blueprints. It would seem we should pop the champagne. We won. We understood everything about light and matter, but there is always a but, isn't there? Right in the heart of this perfect theory, in the very equations that give such precision, sits one constant. One number that we are forced to plug in there by hand. We don't know where it comes from. It just sits there and smirks at us. And this number has haunted physicists for almost 100 years. Great minds have gone mad trying to understand its meaning. Some even turned to mysticism. And here we are. We took magnets apart into atoms, atoms into electrons, fields into virtual photons. We found equations that predict reality with the precision of a hair. But there is one thing I cannot stay silent about: the skeleton in the closet of all modern physics. In the equations that describe light and matter, there is one constant. We denote it with the Greek letter alpha. It is the so-called fine structure constant. What is it? Roughly speaking, it is a number that tells us how strongly an electron clings to a photon. It is the stickiness of the universe. It is the strength of the electromagnetic interaction. You can imagine it as a volume knob on God's amplifier, and this knob is turned to a very specific value. This number is approximately 137. Why? Why not 100? Why not 200? Why exactly 137? You wouldn't believe how much paper we wasted trying to derive this number mathematically. We thought, maybe it's like pi, maybe it's related to the geometry of a circle, but no, it is not derived from anywhere. It just is. It is the weirdest number in physics. You see, most constants have units. The speed of light is meters per second. The gravitational constant has its units. But alpha, it is dimensionless. If we meet aliens from Alpha Centauri, they will have different meters, different seconds, different kilograms. Their speed of light in numbers will be different. But 137 will be the exact same. It is pure magic. It is a number written by the hand of God, and we have no idea how he held the pencil. The great physicist Wolfgang Pauli, the father of that exclusion principle, because of which you don't fall through the floor, he was obsessed with this number. He was tormented by it. He asked, why 137? There is a legend, and it is true. When Pauli ended up in a hospital in Zurich with pancreatic cancer, his assistant came to visit him. Pauli looked terrified. He pointed to the number on his room door. It said 137. He said, I'm not getting out of here. And he died in that room. Why is this number so important? Because if it were even slightly different, our world would not exist. If alpha were bigger, electrons would be attracted to the nucleus too strongly. They would fall onto the nucleus. Chemistry would become impossible. No bonds, no molecules, no DNA, no life. If it were smaller, matter would be too loose to create stars where carbon is forged. The universe balances on a razor's edge, on the edge of the number 137. We know how to use this number. We plug it into our computers, and it gives us the right answers about magnets, about lasers, about nuclear reactions. But we don't understand it. It reminds us that we are still children playing on the seashore. We found beautiful seashells, our theories. We learned to predict the tides. But the ocean is still dark and mysterious. Whenever you feel proud of the human intellect, remember 137. This number laughs at us. It says, you think you figured out the game? You don't even know who wrote the rules. And you know what? That is beautiful, because it means that there is still mystery in the world. So we return to the beginning, to that chair, to that journalist who simply wanted to know why magnets repel. And now, do you understand why I couldn't answer him with one phrase? If I had said, it's as if there were a rubber band stretched between them, I would have lied to you. Because if you ask me, and why does the rubber band contract? I would have to tell you about atoms. I would have to tell you about the electric forces that hold polymers together. Ultimately, the rubber band works for the same reason the magnet works. Explaining electromagnetism via rubber bands is like explaining how an engine works via the wheels. It is cheating. People often think that science kills beauty. They say, you disassemble the rainbow into wavelengths, and it stops being magical. Or you look at a flower and see only cells and reactions, you lose its beauty. Knowledge is not the destruction of a miracle. It is the multiplication of the miracle. When you hold that little magnet in your hand, you are not just holding a piece of metal. In your palm lies the entire history of physics. You feel the force that keeps you from falling through the earth. You hold in your hands the proof of Einstein's theory of relativity, because without it, this magnet would just be a piece of iron. You feel the collective dance of billions of quantum spins aligned in perfect order. And somewhere deep down in the silence between atoms boils an ocean of virtual particles appearing and disappearing, obeying the mysterious number 137. Isn't that amazing? Isn't that better than just saying, well, they attract? I know it is difficult. I know that our brain, which evolved to find bananas and run from tigers, is not very well adapted for quantum mechanics. We feel uncomfortable when we cannot visualize something. We want the world to be a mechanism on springs, but the world is not obligated to be understandable to you. It doesn't care. It is what it is. Our job is not to impose our rules on nature, but to listen to her. And if nature tells us she is absurd, that she is strange, that she is probabilistic, we must accept that. We must learn to enjoy that strangeness. Many people don't like not knowing answers. They are afraid of the unknown. They want to have a ready-made explanation for everything. I don't. I can live with doubt. I can live with uncertainty. I think it is much more interesting to live not knowing everything than to have answers that might be wrong. I have approximate answers and possible beliefs and different degrees of certainty about different things. But I am not absolutely sure of anything. And there are many things I don't know anything about. And that doesn't scare me. To be lost in a mysterious universe full of riddles, that is the real adventure. So next time you see a magnet, pick up a paper clip. Don't take it for granted. Stop. Look at this little miracle. Smile at it. Because now you know what an incredible, complex, and beautiful game is happening right in front of your eyes. That is the pleasure of finding things out. See you tomorrow. Don't be late.